Over a single 12-hour port stay, a commercial vessel might exchange thousands of tons of cargo, load heavy fuel oil, and pump out ballast water. Every weight transfer, from a single container to 1,000 liters of fuel, alters the physical balance of the vessel. Placing a heavy container high on the deck or emptying a water tank deep in the hull changes where the ship's total mass is concentrated. We track mass using the center of gravity, or G, where the ship's weight concentrates. To measure G, we reference the keel, K, the hull's bottom. The vertical distance connecting keel to G is kg, our most critical safety metric. Chief officers are required to predict the final location of G with absolute precision to ensure the vessel remains upright under all sailing conditions. They must account for hundreds of individual cargo moves to calculate the resulting final kg. By calculating these shifting weights, officers transform theoretical physics into a verifiable safety plan that prevents the vessel from capsizing during its voyage. This diagram shows the precise geometric centers of a rectangle, a circle, and a triangle. These geometric centers are called centroids. When we extrapolate a 2D centroid into a 3D homogeneous body, meaning an object with uniform density, that geometric center becomes its center of gravity. If you suspended the object from this exact point, it would balance perfectly. We can observe this physical law in practice. By placing a wedge under the exact center of gravity of a uniform block of wood, the downward force of gravity is perfectly countered by the upward force of the fulcrum. Now we can observe how that balance point reacts when mass is altered, beginning with the removal of weight. These models show that when a chunk of mass is removed from one end of the block, the center of gravity shifts. To maintain physical equilibrium, the balance point moves directly away from the empty space left by the removed mass. This box outlines the mathematical variables governing that shift. The total shift distance is gg1. The weight removed is w, its original distance from the center is d, and the resulting total weight of the object is w minus w. Conversely, these sequences demonstrate what happens when mass is added. Adding weight pulls the center of gravity toward the new mass. The math in the round box remains identical, but we add the new mass into the denominator, calculating total weight as w plus w. Any individual weight change causes a calculable shift in the overall center of gravity. By knowing the exact weight, its distance from the center, and the total mass of the object, you can predict exactly where the new balance point will be. The physics dictating a wooden block on a fulcrum apply exactly the same way to a steel hull floating in seawater. This 4-panel schematic illustrates that reality. Discharging cargo from different holds pulls the ship's center of gravity in specific, measurable directions, directly away from the removed mass. Even shifting a container from the deck to the lower hold is calculated using these same rules. Mathematically, a shift is treated as two distinct actions: discharging the weight from its original position and loading that exact same weight into its new position. But the GG1 formula has a severe operational limit. Using it requires you to calculate a new total mass and a new exact center of gravity after every single adjustment. During a standard port call, a ship loads 500 containers, discharges 300, pumps heavy fuel oil, and adjusts tons of ballast, all simultaneously over a few hours. Calculating a new GG1 shift after each of those hundreds of operations is mathematically inefficient and highly prone to human error. To track stability accurately on a commercial scale, officers use a different system. The maritime industry solves this scaling problem by moving away from individual shift vectors and instead aggregating all forces into a master ledger. This is known as the accountant's method. The core unit of this method is a moment. A moment is a force causing a turning effect. We calculate a moment by multiplying a weight by its vertical distance from the keel, resulting in a unit called ton-meters. Instead of solving formulas in sequence, deck officers track every turning force in a standard tabular layout. The first entry is always the baseline state of the vessel before any cargo operations begin, its initial displacement, its current kg, and the resulting baseline moment. When loading cargo, the physical weight and the newly created ton-meter moment are added to the ledger as positive values. When discharging weight, like pumping out ballast, The weight and its corresponding moment are subtracted from the ledger as negative values. The accountant's method turns the chaos of concurrent port operations into a linear, trackable list of downward forces. Once all cargo operations are logged, the chief officer consolidates the ledger to verify the ship's sailing condition. This table illustrates the final tally. We sum the weight and moment columns to find the total final displacement and total final moments. To find the actual center of gravity, we divide 22,750 ton-meters by 4,600 tons, yielding a final kg of 4.946 meters. The math is straightforward, but discharging cargo invites a common, dangerous error among junior officers. When you discharge a weight, you subtract its mass and its resulting moment. However, its kg distance must never be entered as a negative number. Kg is a physical coordinate in space. A tank sitting half a meter above the keel remains a positive half meter above the keel, whether it is full or empty. The mathematical subtraction is handled entirely by the moment value. With the final kg calculated, the officer can now determine the vessel's stability. To determine if the ship is safe, we compare the final kg to the metacenter, or km. The km is a point that represents the theoretical pivot of the ship's stability, effectively the upper safety limit for the center of gravity. The distance remaining between our kg and the km is known as the metacentric height, or gm. A positive gm indicates the center of gravity is low enough to prevent capsizing. Because our final kg is proven to sit below the metacenter limit, the vessel possesses the necessary stability to sail safely into the open ocean.